Hi all. I apologize that I can't be there in person to give this lecture, but it looks like my flight is going to be canceled, so this is the best I can do. I plan to come to the office as early as possible, and I will be in my office from then until 11:50. And so anyone who wants to come and ask me a question is welcome to do so. Okay, so note that Quiz 6 is due this coming Tuesday. You should be doing the readings in the syllabus, including reading the light side manual. And just as a reminder, there are 4 videos related to the text unit that you should take a look at. And we'll continue the text unit today from where we left off last time. So we're talking about error analysis, and I want to review a little bit because that's really an important topic. It's probably the most important topic of the text unit, and it will be something that will be extremely important on the midterm that's coming up and also on your final project. A big chunk of points will be dedicated to this, so it's a really important thing to do and to learn in this class. So we looked at this example briefly on Tuesday. This is an example I made up about temperature and humidity affecting the decision to play tennis or not. And if you look at the formula that's at the top right-hand side of the screen, you can see that the rule that I used to generate the yeses and nos requires that you consider temperature and humidity together. And if you train a linear model, it's not going to be able to do that. It just considers each separately. So the best linear model that can be learned is y equals 0.29 times temperature plus 0.23 times humidity minus 43. And if y is greater than 0, then it will predict no. Otherwise, yes. But the problem is that since it's considering temperature and humidity separately, what it's going to end up doing is to set the thresholds for temperature and humidity lower than 75, and it isn't going to consider them separately. It'll just consider them. It isn't going to consider them together. It just considers them separately, and so it misses some conditions where it should predict yes. It's going to actually make both kinds of errors. Sometimes when it should say yes, it'll say no, and vice versa, and we'll see that. Now, I started to talk about error analysis having 2 kinds of comparisons, and today we're also going to look at that in light side. So I want to remind you again of the idea. We know that in a confusion matrix, like what you see on the left-hand side of this screen, the columns represent predictions that a model made, and the rows represent the actual labels. And so the downward diagonal is the correct classifications, and all other cells are error cells. So the 25 instances here are instances that should have been A but were predicted as B, and the instances here are instances that should have been predicted as B but were predicted as A. And there are 2 explanations for why instances end up in the wrong pile. It could be because they look different from what they are, or it could be because they look similar to what they're not. But what we want to do when we build representations for machine learning is make instances of the same category look similar to one another, and instances of different categories look different from one another, and we have some choice over how we do that when we design our representations. So the first comparison is the vertical comparison, and here we're comparing the 25 instances that ended up in the top right-hand side error cell with the 149 underneath them that were correctly classified as B, and what we want to know is what are the features that make those 25 look like B. And so feature by feature, we're going to compare the extent to which those features in the 25 are in similar distribution to what they are in the 149, and that will be computed by subtracting the average value of that feature and then taking the absolute value of that difference. And the reason why that makes sense is if we were assuming a normal distribution, you could summarize the distribution using the mean and the standard deviation, but the mean is a really important one of the parameters, and so we're using that as a stand-in. Now, in fact, the value of that feature may not be normally distributed, in which case this comparison makes an assumption that's not valid, and that can often happen, and then it may give you misleading information. That's true. The horizontal comparison is different from the vertical comparison. Here what we're looking for are features that make the 25 look different from the 44 in the cell next to it. And so here we're going to do the similar subtraction, and take the absolute value again. But what's going to mark a feature as problematic here is that it has a big value once we do that. And that's because we want to see features that are in different distribution between the 44 and the 25. And because those features in different distribution between those sets are features that make the 25 look different from the 44. Now if we go back to our spreadsheet, we can see, based on the best fitting linear model, what are the actual values and the predicted values, and we can sort based on actual and predicted and see which instances are in which error cell or correct value cell. And we can take the average value then of each of our features within those sets. So this 93.765555 is the average of all of the temperature values in the set of ones that should be predicted as no and were correctly predicted as no, whereas the 87.43 is the average value of all of the humidity scores in that same cell, and so on down the line. So in that case, based on the same math that I told you about, we can compute the horizontal comparison for temperature and humidity for our two error cells, and also the vertical comparison for temperature and humidity for our two error cells. Now on the horizontal comparison, as I said, a feature is problematic if it has a large value, and so we can see that humidity is a good place to start for our troubleshooting because it has the largest horizontal comparison value. So that's for yes, things that should be yes and that were predicted as no. So that's here. And if we're doing a horizontal comparison, those that are actually yes and predicted as no, we're going to compare with the 18 that were yes and predicted as yes. So we see that what we're comparing are the things in this set of 2 with the things here in this set of 7. I think it may be that not all 7 of them are showing. Oh, actually 18, sorry, should be 18. See that here. But they're not all showing. Okay, so if we're going to, so what it's telling us is that the humidity value makes these 2 look different from the 18. So if we look, we can see the humidity value here is relatively high, and in fact the humidity value in the yes set is low, and similarly on average the temperature value. Now what is it that we need to notice here that would tell us? Well, those instances that have high humidity values are mostly up here in the set that are no and predicted as no. But if you look at their temperature value, those are also high. And if you look at the temperature values here, they're low. And so what makes these not like those ones is the fact that temperature is low. And so what that tells us is that the high humidity values here are ambiguous. Sometimes when humidity is high, it does mean no. But other times when humidity is high, it doesn't have to be. Or these don't look the same as these. These look more like the cell where they should be. And so that already starts to make us think. Now, what we see here in this information, the error analysis points us to noticing these things, but it doesn't tell us how to fix it. What tells us how to fix it is that in our own head, what this should trigger is to think, oh, well, it's true, these are highly humid, but the temperature is low, and actually on a day with the temperature is low, even if the humidity is high, it's not that bad. And so then that could inspire us to add a new feature that looks at temperature and humidity together. So the problem here is that the linear model can't see the connection between temperature and humidity, and we need to fix that somehow. So here's kind of an explanation of that that's a little bit long. I left that in here so that you could step through it on your own if you want to. So the slides that are posted have this text. And it's a little bit like the exclusive OR case. In this case, you could think, the 2 input nodes, they're like temperature and humidity, and we saw that we weren't able to correctly handle the case where they were both 1. Which is different from the case where one is 1 and the other one is 0. And that's similar to where we're at with our heat and humidity example. We need to understand that two of them together is different than one of them by itself. And the way we fixed that before was to add an intermediate node. And we said that there are two ways that you could do the equivalent of adding this intermediate node. You could either go to a nonlinear model, or you could add a feature, an interaction term, something that combines across those two inputs so that they're not being treated separately. So you can see here I have added a feature, and that feature is in the combine column. And this feature essentially says if both heat and humidity are higher than 75, then put a 1 here. So we do. And you can see that by some easy computation, we can have a feature that's very distinguishing. It entirely correlates with our class value. So it somewhat fixes the problem. But even if we didn't add that feature, if we went to some nonlinear model like decision trees, then again, we get a much higher performance. Here we only have 2 errors in our confusion matrix. Or if we use SVM with a nonlinear polynomial kernel, again, we get a substantially higher performance than we would in a cross-validation with just the 2 features separately on a linear model. In that case, I didn't show it here, but you can try it yourself. You would end up getting a negative kappa. So we can expect the text features would be even more confounded here, and so the process would be a little bit less straightforward in terms of how to fix it. So I created a data set. I added some text to each one of these examples, and then I tried to classify as yes versus no only based on a unigram model extracted from that text. And in most of the cases where the word I appeared, the text was for play equals yes, but I ended up being a feature that had a high weight and a high horizontal difference. And so it's very likely to be something that was causing a substantial number of errors in the cell for ones that should be no but were predicted as yes. And so if we go down to the documents display, so let me just say slowly how to set up this interface, the error analysis interface in Lightside. We're going to go through it again later for a more extensive text example, but I may as well explain it as long as we're here. We've got our confusion matrix. We want to click on the radio button for the cell that we want to explain errors in. Down below where it says evaluations to display, we want to select columns frequency, horizontal absolute difference, vertical absolute difference, and feature weight. The reason why we want to do that is because, first of all, we've already talked about the vertical comparison and the horizontal and vertical comparison. Frequency matters because even if a feature is problematic, but it almost never occurs, then if you fix that problem, it's not going to have much of an impact because it's only affecting a few examples. And on the weight, if the weight is not substantial, then that means the model's ignoring that feature anyway. So again, fixing that problem isn't going to help you very much. So we want to find ones that either have a high horizontal difference or a low vertical difference, have a relatively high frequency, and have a high feature weight. Here you see the frequency is 3, and you might say that's a definition of high that I've never heard before. But considering that there were only 7 instances in that cell at all, then 3 is almost half. Okay, so then we go down here to Exploration Plugin. We're going to select Documents Display. We're going to check Filter Documents by Selected Feature and Documents from Selected Feature. And then we can see the instances that meet this requirement. So these would be the instances that have the word I in this cell, and there are 3 of them. And then we can look at the text and it will highlight the I's so we can see where they are. And we see that these, where I is being used differently, whereas something negative is being said. It's really a complaint in these cases. And if you looked at where I was occurring in the correct error cell, or the correctly classified cell that's related to this, you would see that those I's are more about things that I would do. They're things that show a positive attitude towards playing tennis. And so the word I itself is actually just being used as a proxy since more often than not when there was an I sentence in this data set, it was for play equals yes, it ends up being a proxy for having a positive attitude towards playing tennis, when in fact I doesn't mean anything of the like. And so it's a proxy that it doesn't make sense to anyone, but it does make sense to a machine learning algorithm. And so then it ends up being a feature that gets weight. And the answer is that what we need to do is create a richer feature that that more correctly represents how I is being used, or something other than I that correlates with I, that can draw weight away from I and onto something that's more valid, that's really the complaint in these cases, or that's really the positive attitude, the thing that somebody might do in the other sentences. Okay, so that's kind of a contrived example, and now I'm going to get into a more realistic example for you. And that's going to be looking at these two movie reviews, a positive one and a negative one. And what you're going to want to do is kind of look through this. You want to pause the video at this point and look for words that are either positive or negative in either one of these reviews. So stop that and then come back here after you've done that. So underline the positive words that you see and circle the negative words that you see, or make a list of them somewhere if that's more convenient from where you're sitting, and then come back. Okay, if you're coming back from having paused, now when you look at these examples, what you can see is that although you might expect that the positive review has positive words in it and the negative review has negative words in it, words out of context sometimes that are being used negatively don't end up being words that are negative per se, and vice versa. So sometimes even you'll see a word that has no positive connotation, but it could be used positively, just not in this context. You could see a word that was meant very positively in this context, but out of context that word doesn't really have a positive or negative association. You could also see a word that's being used negatively in this, but you wouldn't see that word by itself as being negative. And similarly, you could have a word that is usually negative but not being used negatively here. So there are lots of misleading things that can happen in text when you go down to a unigram feature space. Now, it's still the case if you have enough text that oftentimes whatever occurs most frequently, the most in a movie review, if you have mostly positive words or mostly negative words, what ends up being the case is that that becomes a relatively good predictor of a negative versus positive review. But that's not enough information, it's misleading information, and you'll run into lots of problems like we saw with I. So here's a closer look at the positive review. Here's a closer look at the negative review. So spend a little bit of time playing around with that. Now, as we did with the questions and statements, if you look at these two examples, you will start to get a sense for what you might expect features to need to look like in order to do a better job than unigrams when you're classifying positive or negative. And we're going to do a lot of work with the sentiment sentences data set. So in that case, we'll be looking at shorter pieces of text, but they're extracted from the same data source, so they will be of the same nature. And so whatever ideas you get from this exercise, you can then apply in your work with the sentiment sentences data set, and that would be a good use of this activity. If I was there, we would have done it together in class. Okay, so now I want to introduce you to an idea of a different feature structure, something more powerful than any of the ones we looked at in class on Tuesday. And so we're going to talk about the Stretchy Patterns paper. It was the supplementary paper for this week that was on Blackboard, and it was published at a workshop at EMNLP when it was in Scotland, I think. And some students did this as a class project in one of my other classes, a discourse analysis class, and then they decided to make it part of Lightside, and I think it's a pretty useful feature extractor. So the paper, it was applied to a data set that was this blog authorship corpus. I think it's even one of the data sets that you can get on Canvas if you look at the sample data sets. So it's something that you could use for your project if you ended up wanting to do that. In this paper, we just looked at a subset of that data. There had been some papers that were published. You can see here, Schlur 2006 was one of those papers that actually claimed to have gotten very good performance on this data set. So this data set is a huge set of blog entries where every blogger is indicated by their gender, their age, their occupation, and their astrological sign. And so you can use it as a text classification problem to predict any of those 4 variables. Not surprisingly, it's very difficult to predict someone's astrological sign from their blogs, but the other ones are somewhat predictable. But there had been some papers that claimed to get very high performance on gender prediction from these blogs. But even if you look at the list of words that were most indicative of male and female from their paper, you can see that they're really not style words, not things that really describe any differences between how men and women talk or write, but really just different things that they talk about. And so they were claiming that they were able to do this style detection related to gender as a variable. And so in our paper, what we were looking at was 2 things. One was investigating whether it was really gender that they were picking up on, but also thinking what would be a richer representation that might pick up better on style. So there's been a lot of research in other fields than language technologies on how men and women supposedly talk differently. Some people would consider women's language more varied, more creative, kind of deviant in comparison to male language. So also people have compared the female style more to narrative or storytelling, whereas men quantify more and seem more like nonfiction. There also seems to be claims that women use more hedges or qualifiers or intensifiers, that they sound less certain and more emotional than men, and they use kind of immature little markers like maybe they just are more likely to have come from California like me. Just kidding about that, actually. But if you listen carefully to me, you'll see I insert like in inappropriate places, and I don't believe that it's related to my gender, but that's just a side comment. All right, so it's also the case that those features of speech that supposedly distinguish male and female speakers are confounded with other variables, and in particular the male versus female variable is confounded with age, so men sound older on average than they are, and women sound younger on average than they are when we consider both of these. And interestingly, with this data set, we have the ability to take those into account simultaneously, since we have both of those indicators. And I already mentioned the thing about men sounding more like nonfiction when women sound more like fiction. So it's problematic that these features are confounded with one another, because if you really want to isolate one of these variables, and the other variables are varying as well, and if they're not marked in the data, then what you don't know is how those other variables are contributing to the same features that you're looking at in order to predict the one that you're interested in which case your coefficients will be adjusted for whatever balance between those other variables you have. And if that doesn't hold in whatever data you are applying the model to, then the adjustments that are made for those differences in distributions won't carry over. So this slide really just explains that. If you want to pause and read it, that would be fine. And then we can move on. Okay, so look at this slide here. This is kind of a graphical representation of what I just said. Let's imagine that each one of these 3-letter words here is indicating 3 different variables. The first one, F versus M, is female versus male. Y versus O is young versus old. H versus L is high socioeconomic status, low socioeconomic status. And let's say that what we're trying to do is use the extent of swearing to be able to predict male versus female and train versus test. And because we know that men have been claimed to swear more than women, and so that should be a good predictor. So we've got the female versus male label. Let's say that the young versus old and high versus low socioeconomic status variables are not indicated, but there's a particular balance of those in the training set. In particular, there are no males that are old and high socioeconomic status in this data set. And we know that age and socioeconomic status also affect the extent of swearing. And what that means is that the model as trained on this data set is going to overestimate the amount of swearing that men do, because men who swear less, the older, high socioeconomic status men, aren't represented in this training set, whereas they are in the testing set. So those men who are old and have high socioeconomic status in the test set are likely to be mistaken for females, because the level of swearing is less than what is expected given the mix of age and socioeconomic status in the training set. So that's a problem when we use features that act as proxies, because it's often the case that those proxy features vary along multiple different variables, some of which are explicit in our data and some of which are not. And so there's a lot of, just as I said, implicit adjustment to the mix of those variables in the usage of the proxy. And the only way to get around that is either to just be very rigorous in terms of what other variables you control for, but that requires having access to those variables, or you can use features that are less low level, that are less like proxies and more like valid indicators of whatever it is that you are trying to predict. So stretchy patterns was our initial attempt to have more valid features than unigrams or biograms or part of speech biograms. And so what is a stretchy pattern? If you look in the light side user's manual for stretchy patterns, you'll see there are these template patterns. They have a size, which is the pattern length that you see. You get to indicate the size. That's how many symbols make up each pattern. And each pattern is kind of a pattern that's going to be matched over the text. And then when that pattern is matched, if the pattern does match someplace in the text, the value of that feature for that instance becomes 1, otherwise it's 0. And we'll look at some specific examples. Actually, maybe we'll just do that now. So, and then we'll go back. If you look in the lower right-hand corner, you can see some stretchy patterns. You can see the first one, B, gap, strong neg, has 3 symbols, so that's its size. You can also see that it has a gap in there, and gap is why they're called stretchy patterns, because the gap allows the pattern to skip over some words that don't have to match something explicit in the pattern. And then elements that are in all caps are the names of categories, and we haven't talked about categories yet, but we will. And so those stand in for a list of words. So you can see that these lists, these feature patterns, they might look like trigrams. There are even some fourgrams in there towards the bottom, but they actually represent more than a single trigram. Because they can stretch over some words, and because the categories can match any of the words in a particular list. And so because of that, what we can do with them is they can be long like trigrams, but not as sparse as trigrams, because they match more than just one sequence. So B, gap, strong neg could be is very extremely terrible, or it could be is slightly bad. Both of those would match B, gap, strong neg. So there are lots of different strings that might match. And so whereas the problem with trigrams was when you add them, they're less ambiguous than a bigram or a unigram, but they're more sparse. That's not necessarily true of these stretchy patterns. We still have the problem that we add a huge number of them when we use stretchy patterns, but at least they're less sparse. Okay, so going back to where we were. So stretchy patterns have a length. You get to set this range that says how big those patterns can be in terms of numbers of elements, and the gap and categories and words all count as elements. And then you get to say what is the range on gap length. That's how many words can be skipped every time you see the word gap. And then you get to decide other things like Can some of those symbols be just specific words? Can some of them be part of speech tags? And you can add categories, which you can make yourself. Now, LightSide comes, and you can see the path to where this categories folder is in your LightSide folder. These are just text files. The name is the name of the category. If you look in the text file, you can see that the first row is the name that will appear in the stretchy pattern if that category is used, and every line after that is an element of the list, so you can define your own categories, which are lists, and that's a very useful thing that you can do to extend the power of these stretchy patterns. So there's a list of categories that exist so far, so we can get strong neg out of here. It's a list of negative words, and we can add that as something that can be included in one of our stretchy patterns. You can also check that you will require at least one category in each pattern that's created, and that's a good thing to do because then these categories kind of anchor the patterns that get induced. And there are some other things that you can use to specialize. And so if you extract these, then you can scroll down and see the features that you added to your feature space for the stretchy patterns. Now in the paper, we did a very controlled evaluation of different feature spaces and how useful they were for gender classification. And so one of the things we did, since occupation was a variable that was indicated and people often talked about their job, and because in the original experiments, the gender balance under these jobs was very skewed, we set up a more rigorous evaluation where we took the top 10 occupations and we sampled evenly from those men and women so that occupation wouldn't be confounded with gender in our evaluation. And then you can see that we had a unigram feature space as one of the feature spaces we evaluated, unigrams and bigrams, part of speech bigrams, and then stretchy patterns. We did two kinds of evaluations. Where it says average, what that is average on a leave one occupation out cross-validation. So in that case, what we would do, for example, is if we were going to test on people in the engineering field, we would train on all other 9 occupations and see how it generalized to engineering, so that we wouldn't learn to just associate engineering with a particular gender. And we would also see how those features that distinguish between genders in other fields also distinguish between gender in the engineering field. So it was a very stringent test of generality, and in this particular row you can see that unigrams plus bigrams, and part of speech bigrams are about random. They're just around 50, and they aren't significantly different from 50, whereas we're significantly better than 50 in the case of stretchy patterns. But it's still not great, but at least it's not random. Random cross-validation instead does a random cross-validation. In that case, we at least have an even distribution of genders within the different fields, but we could still learn what specifically distinguishes male-female within a field and use that to make our prediction. So for example, if it's true that in education men and women take up different kinds of positions, then in train and test we could learn from train how to distinguish between those positions and test and use that. And so then we do a little bit better than random in this particular evaluation setting for unigrams plus bigrams, and part of speech bigrams, but we do even better with our stretchy patterns. So besides the introduction of stretchy patterns as a type of feature extractor, this paper is a good example contrasting two different evaluation methodologies. Random cross-validation is what we usually do, but leave one occupation out cross-validation is the kind of cross-validation we can do easily in LightSide, and it's called cross-validation by annotation in LightSide, and the annotation in this case would be occupation. And so we wanted to have that so that if we were doing an experiment like this, it would be easy to set up in LightSide. So here again, I'm just highlighting the distinction between these two evaluation methodologies. You can see how we really get a different story about the comparison across these different feature spaces when we evaluate things differently. So we get a slightly rosier picture from a random cross-validation than a more stringent cross-validation by annotation. So only stretchy patterns can hold up to the most stringent of these evaluations and show us a non-random performance. But that's not to say that we think that these stretchy patterns are the be-all and end-all. There's some discussion about them as in terms of what kind of style they're actually picking up on. But we weren't happy with this like basically 54% that we got. So we don't want to overstate that at all. All right, so now we're going to think about error analysis in a sentiment analysis data set. And so the idea is that this is going to illustrate an iterative process of starting out with a simple baseline, doing an error analysis and revising and evaluating again and so on. And we're going to use our horizontal and vertical comparison, or vertical and horizontal comparison, as I just showed. So in this case, we are going to take our data set, the sentiment sentences data set, and we're going to divide it. And we're going to divide it into a cross-validation set and a development set. And the reason why we're going to do that is now I'm going to illustrate to you how you should really do error analyses with your project data, where you will have a development set, a cross-validation set, and a final test set. So on the front panel of LightSide, you're going to want to load the cross-validation set. And you're going to do the feature extraction from that. Then to set up for the error analysis, you're going to load the dev set on the build models panel. And then you're going to train on the cross-validation set and test on the dev set. And then that will allow you to do the error analysis over the dev set. And you're going to set it up just like we did on the very simple example before. We're going to click on, so you're going to pick in a pull-down menu the experiment where you trained on the cross-validation set and tested on the dev set. Then you're going to click on the radio button for the cell that you want to explain the errors in. Then you're going to add the frequency column, horizontal absolute difference, vertical absolute difference, and feature weight. And when you're going to look at these horizontal, so let's look at the horizontal comparison first. You're going to want to sort everything by this horizontal comparison column. So click in order to bring the high numbers up to the top. And if it turns out that it does the opposite and brings the small numbers up to the top, just click again. So then we will have sorted. And then what we want to do is kind of look for some feature that's promising to follow up on. And the word "you" seems somewhat promising. And the reason is because it occurs 37 times, which is a non-trivial number of times. It has a relatively high horizontal absolute difference, and the feature weight is high. So we want to explain to you that's what we want to do. And so we're going to then select Documents Display, click on Filter Documents by Selected Feature and Documents from Selected Cell, and then we'll get all of those examples and we can see where "you" occurs. And similar to the I case before, you'll see that one of the things about "you" is that oftentimes "you" sentences in these are recommendations. And oftentimes they are positive recommendations, but sometimes they're negative recommendations. And so "you," because more often than not when a recommendation is made, it's that you should see this movie, which is positive, "you" becomes associated with positive. But "you" isn't inherently positive or negative. So we want to draw the weight away from "you" by making it more context sensitive so that it can learn to distinguish "you's" in contexts where it's a positive recommendation from those where it's a negative recommendation. And we're going to use stretchy patterns to do this. And so we're going to anchor our stretchy patterns on second person pronouns, as you can see. And then we're going to run our experiment, and it turns out that's not significantly better. So that didn't really work, even though it was an idea that was motivated by what we did. And it turns out that the problem is that it just induces such a large number of features that the feature space becomes too big for the number of instances. So now we can try a different configuration of the stretchy patterns. And this different configuration actually anchors not on "you," but on positive or negative words. And in that case, we get a marginally significant improvement. And it's equally motivated by the pattern that we saw. It's just a different way of solving that problem. This way of doing it worked well. We could also try something even more simple, which is just using unigrams and bigrams instead of just unigrams. Again, it gives us a little bit of context sensitivity. It adds a lot less number of features to the feature space, and you can see that that gives us a more striking improvement, a statistically significant one. Now you're going to want to also be able to do error analyses with non-text features, and I think that we'll probably finish our lecture after this part of the content. So let's say you have a feature space that has some numeric values. So how would you add those numeric values to your feature space? You can use column features. So here we're loading a data set. It has some non-text features. Like usual, we are selecting our class value, and then we check the column features extractor. We've unchecked basic features because there are no text fields, and so of course nothing is selected over on this side where we would have checked off the text fields. And instead, we're going to configure the column feature extractor by checking each one of the columns. And these would be columns in our CSV file that we want to have in our feature table. And so when we do the extraction, these are added to our feature space. So just like before, we can do a logistic regression experiment so that we can see the extent to which we can fit a model to make this prediction, and we get mediocre accuracy and relatively poor kappa. And so now we can go ahead and do our error analysis. One thing to note is that in order to do this in a valid sort of a way, we would want to actually do, we would want to normalize our columns of numeric features so that they all have the same range, because otherwise the values that we get for horizontal and vertical comparison won't be valid. For ones with bigger ranges will have higher horizontal and vertical comparisons and vice versa, and that's not what we want. We want to know more precisely, differences in distribution, not the differences in range. So we have to normalize the ranges, and this example, I think, does not do that. And so, but when you do it, that's what you should really do. So here is an example where we did that normalization, so you can see how it's done. And there's a couple of different ways that you can do this, and you should definitely do that with your data so that you get a good indication for the horizontal and vertical comparison. And here in this slide, it explains to you what you just saw on those slides from Excel. You could either just use the formulas as I've shown them on those slides, or read through this text to guide you through doing that. And then you're able to do the horizontal and vertical comparison just as you would have. Now, what you can't do is look at the texts when you're following up. So it's hard, you can't use the documents display the way that you would have. So in our next lecture, I will come back and talk to you more about how to do an error analysis for non-text data. But we're going to stop here for now. So if you have questions about this lecture, go ahead and post them to Piazza. And like I said, I'm going to try to come to my office when when flight gets in, and I will post to Canvas, through Canvas, to send you an email when that time comes. And so then you'll be able to come to my office and ask me questions if you want to. Office hours for the rest of the week will happen just as they are usual, and so hopefully you can get all of the help that you need. And again, I'm sorry for this inconvenience that it looks like my flight is going to be canceled. Talk to you later.